Welcome to the deep dive. If you're listening to this, you're probably a lot like us. You know, you love the pursuit of knowledge, you want to be the most well-informed person in the room, but you absolutely dread that feeling of information overload.
Oh yeah, completely. It's overwhelming.
Right. There is just so much data out there, and so we increasingly rely on AI to kind of cut through that noise for us. But, well, here is the terrifying question that we are tackling today. Imagine your new AI data agent summarizes a massive financial report for you, and it confidently declares, Q3 revenue grew 12.3%.
Which sounds incredibly helpful.
Yeah, it sounds great. But how do you know it didn't just, invent that number out of thin air?
And that right there is, that is the core vulnerability of the entire generative AI landscape right now.
Huh.
We have these models that are undeniably incredible at generating human-like text.
Hmm.
And they're even getting quite good at writing code.
Yeah, the coding abilities are wild.
They really are. But when we push them into data-heavy analytical tasks, the kind of tasks where a single hallucinated decimal point can ruin a quarterly strategy, their internal reasoning becomes a complete black box.
It's totally opaque.
Exactly.
Yeah.
We are trusting these systems with crucial, high-stakes decisions, yet we have almost no capacity to audit how they actually arrived at those decisions in the first place.
Which is exactly why we are dedicating our time today to a foundational piece of state-of-the-art research that is quietly rewriting the rules of how we interact with technology.
Yeah, this is a big one.
We are unpacking a June 2026 paper from Renmin University of China called VeriGraph towards verifiable data-analytic agents.
It's a fantastic paper.
It really is. So the mission for this deep dive is to understand this massive paradigm shift in computer science. We are moving away from AI that simply hands you an authoritative-sounding answer, and we're moving toward teaching AI to actually show its work in a format that you and I can explicitly verify.
And to really grasp why VeriGraph is such a fundamental breakthrough, we have to look closely at the mechanics of the status quo.
Right, how things work right now.
Exactly. So the current standard for large language model agents, things like React or Kodak models, they operate on what is known as a linear trajectory.
A linear trajectory.
Yeah, it's basically a continuous flat loop of thought, action, observation.
Oh.
So the AI writes a thought about what to do. It writes some code to execute that thought. It observes the result printed out by the code, and then it just writes another thought.
Okay, let's unpack this a bit, because that linear process, it sounds logical on the surface, but it hides a really massive flaw.
It's a huge flaw, yeah.
So think of a stand-in AI agent, like a brilliantly talented chef who comes to your house to cook a complex multi-course meal.
Okay, I like this.
Right, so they do all the work in the kitchen, they plate a beautiful dish, and they bring it to your table. And you ask, are there peanuts in this?
An important question for a lot of people.
Very important. But the problem is, the second the dish was plated, the chef threw away all the grocery receipts, burned the original recipe, and washed all the pans.
The whole process is just gone.
It's totally gone. So the chef just looks at the final dish, guesses based on the vibe, and confidently says, nope, no peanuts. You might get lucky, or you might end up in the hospital because the chef can no longer verify their own work.
That captures the danger perfectly. In a linear AI agent, the recipe and receipts, those are the deterministic computations.
The actual math.
Right, the actual raw math being done by the Python code. But the agent itself operates in a semantic space, meaning it is just predicting the next word in a long string of natural language text.
It's basically a fancy autocomplete.
Exactly. So when Python code runs, it spits out a number, the AI reads that number, pastes it into its text-based context window as an observation, and then it just moves on.
It just drops it.
Yeah, the intermediate code variables, the actual programmatic provenance of that number, they simply disappear into the ether.
The math literally evaporates the moment the code finishes running.
Yes.
And the AI just has a text note left behind that says, the answer was 4.
And this entanglement of raw math and semantic text, that is exactly where hallucinations breed.
Because it forgets how it got the 4.
Right. By the time the AI gets to the end of its linear thought process and tells you to prioritize a specific strategy, it is a massive wall of text detailing its supposed reasoning.
But it's just text.
Just text. And because the underlying math evaporated, you cannot separate real verifiable computation from AI confabulation. The evidence is just a flat transcript.
Which is a nightmare for auditing.
Oh, it's incredibly difficult.
Yeah.
If you are auditing the system, it's almost impossible to distinguish a mathematically sound insight from something the model just confidently made up to satisfy your prompt.
So if a linear, flat timeline of thoughts is the root of the problem, then the solution has to be structural, right? We can't just ask the AI to think harder. We have to actually change the shape of how it thinks.
Yes, exactly. And the researchers at Renmin University, they recognize that data-intensive reasoning doesn't naturally happen in a single flat line.
Right.
It actually exists in two coupled spaces. There's a deterministic code space where rigid math happens, and a semantic reasoning space where flexible logic happens.
And those usually don't mix well.
They don't. So to bridge the two without losing that audit trail, they built VeriGraph.
Here we go.
Yeah. So instead of allowing the AI to spit out a linear stream of text, VeriGraph forces the AI to incrementally construct what they call a heterogeneous evidence DAG as it processes the prompt.
Okay, let's demystify that a bit. Get out of the computer science speak for a second. So a directed acyclic graph, or DAG, is basically a highly organized family tree for data.
That's a great way to visualize it.
Right, so information flows in one single direction. It starts from the raw data at the roots at the very bottom, moves up through branches of math and logic, and arrives at the final answer at the very top. But you use the word heterogeneous, meaning it's mashing up completely different types of data, like raw CSV files, Python code, and plain English sentences into the exact same graph.
Yeah, that is the defining feature of VeriGraph. It is weaving completely different data types into one unbroken chain of custody.
That's wild.
It is. And to make the AI actually build this structure, VeriGraph embeds specific tools, they call them expansion primitives, directly into the agent's code.
Okay, so if I'm trying to build this family tree, keeping the math from evaporating, that seems like the first major hurdle. How does the graph capture a computation without just, turning it back into text?
Right, so it does that through the first primitive, which handles computational expansion. And this operates almost entirely under the hood.
Okay.
Whenever the AI writes and executes code to solve a piece of the puzzle, VeriGraph automatically traces the variable dependencies.
So it watches the math happen.
Exactly. It maps exactly which raw data nodes fed into which mathematical operations. And then the executable code itself becomes a permanent structural branch on the tree.
Oh, wow. But, math alone isn't really an insight, right? A node that just contains the number 4 doesn't actually mean anything to a human analyst reading the graph. The AI still has to interpret that number.
Which is exactly why the system introduces a grounding expansion. In the code, this is referred to as the bind function.
The bind function?
Yeah, and this is where the deterministic math crosses over into human reasoning.
How so?
Well, the AI is forced to explicitly anchor a computed mathematical value to an atomic natural language claim. So instead of just, say, calculating a mean and moving on, the AI creates a new node that ties the computed variable directly to the English phrase, the mean is X.
So it literally binds the human-readable text to the executable code that generated it.
Exactly. It locks them together.
Okay, so we have our raw data at the roots. We have a branch of math permanently saving the computation. And we have a node linking that math to a plain English sentence. So we've established facts.
That's verifiable facts.
But how do we get the AI to actually make a decision based on those facts?
That requires the third tool, which is derivational expansion, or the infer function.
Infer, got it.
And this handles the leaps of logic. When the AI needs to derive a brand new claim from its established premises, it uses this function to connect previous claim nodes to a new, higher-level conclusion node.
Okay.
And crucially, it has to provide an explicit, written justification for that specific leap.
All right, this is a lot of abstract architecture. Let's round this for you listening by walking through a real-world example straight from the paper.
Yeah, the warehouse case study is perfect for this.
Let's do it. So they call it the warehouse restocking case study. Imagine you are a supply chain manager, and you ask this new AI agent to evaluate 3 locations. You've got warehouse A, warehouse B, and warehouse C, and you want to know which one needs immediate attention.
Right. And if you asked a standard linear model this question, it might, crunch some numbers in its hidden Python environment, drop the variables, and then just spit out a text box saying prioritize warehouse A.
And you have absolutely no idea why.
None. But with VeriGraph, the process is structurally transparent from the start.
So how does it begin?
First, the AI pulls the raw data into the root nodes. So it notes that warehouse A has an inventory of 120 units and a daily demand of 30 units.
Right. And then it uses that first computational tool, the compute function.
Mm-hmm.
It writes the code to divide the inventory by the demand. So 120 divided by 30 is 4. It has 4 days until a stock out.
Exactly.
It also pulls the lead time, how long it takes a delivery truck to restock the warehouse, which let's say is 6 days. The math shows a clear gap. Warehouse A will run out of stock 2 days before a shipment arrives.
And all of that math is permanently saved as intermediate compute nodes.
Right.
Now, the AI has to make that math legible, so it uses the bind function.
The second tool?
Yep. It creates a new node that binds that mathematical gap of 2 days to a natural language claim. It officially registers the statement, warehouse A runs out 2 days before refill.
And I'm assuming it repeats this entire process for warehouses B and C, building separate branches for each of them.
Yeah. Exactly. Separate, verifiable branches.
And to finally answer your prompt about which warehouse to prioritize, it uses that third tool, the infer function.
You got it.
It takes that bound claim about warehouse A, compares it to the bound claims it made for B and C, and explicitly derives the final conclusion. Prioritize warehouse A for restocking because it has the highest risk of a stockout.
And because the output is a DAG, the auditability is completely localized.
Which is huge for the user.
It's everything. An auditor or just a manager trying to verify this suggestion, they can look at that final recommendation, click on it, and literally trace the visual lines backward.
You can just follow the path.
Yeah, you see the logical inference comparing the 3 locations. You follow the line down to the bound claim about warehouse A's shortage. You follow that line down to the exact division problem. And then you follow that line straight into the raw inventory data.
So if the AI made a mistake, you don't have to read a massive 500-word wall of text to figure out where it got confused. You just follow the branch to the exact node where the math failed or where the logic took a bad leap.
Exactly. The structure is undeniably brilliant for human verification. But getting an AI to actually build it presents a massive technical challenge.
Right, because an LLM is basically just a highly advanced pattern matching engine, right? It's designed to predict the next word in a sequence. Getting it to consistently follow strict architectural rules without reverting to just writing loose paragraphs of text, that sounds incredibly difficult.
Oh, it is. Designing the architecture is one thing, but training an LLM to adhere to it, that seems almost impossible at first glance.
Because standard reinforcement learning, or RL, operates on a pretty basic premise. It rewards an AI for getting the final answer right. If it gets the right answer, it gets a mathematical reward, like a treat. But if we only reward the final outcome, what stops the AI from just building a massive, useless, bloated graph that accidentally ends with the correct number? Or worse, what stops it from hallucinating the entire middle of the graph just to reach the conclusion it thinks we want to see?
Those are the exact pitfalls of outcome-only reinforcement learning. It leads to a known phenomenon called reward collapse.
Reward collapse.
Yeah, the AI basically learns to hack the system. It realizes that the easiest path to the reward is to just guess the answer using unsupported claims, rather than doing the hard work of actually building a mathematically sound proof.
It takes the lazy route.
Exactly. So to prevent this, the Redmond University team had to completely rethink the training process. They used a 2-stage curriculum.
So they didn't just throw the model into the deep end with a complex problem and a reward function. They had to warm it up.
Right. They started with a cold start phase called trajectory distillation.
Trajectory distillation. Okay, what is that?
Well, if you just give an untrained model these graph-building tools, it will thrash around randomly. It won't even know how to form a valid node. So they used a much larger, smarter teacher model to generate tens of thousands of perfect examples of graph building.
Ah, okay.
They fed these structural templates to the AI to teach it the basic syntax. They taught it how to use the compute, bind, and infer tools before they ever worried about whether it was solving complex supply chain problems correctly.
So it's kind of like teaching a kid the rules of grammar and sentence structure before you ask them to write a persuasive essay on macroeconomics. You know, they have to know how to hold the pencil first.
That's a perfect analogy. And once the model understood the syntax of the graph, the researchers moved to the second stage, graph-based policy optimization.
Okay.
And the genius here is how they designed the reward system to prevent that reward collapse we talked about earlier.
So they changed the grading rubric.
Exactly. Instead of one big reward at the end, they built a 3-part composite grading rubric that perfectly mirrors the layered architecture of the graph itself.
Well, if I'm building this grading system, checking the code seems like the easiest part. How does the first grade work?
The first component is called our process, and it evaluates computational integrity.
Does the math work?
Right. It simply asks, did the Python code actually execute without errors? Did it crash? Did it call a variable that doesn't exist? If the math fails, the branch dies right there, and the AI gets penalized immediately.
Oh, wow. So it's strict.
Very strict. It forces the model to write stable, executable code every single time.
But if you're only checking if the Python code runs smoothly, what stops the AI from writing flawless, bug-free code that has absolutely nothing to do with the problem and then just hallucinating a totally false conclusion anyway?
And that is the exact vulnerability that the second-grade Rinfer is designed to catch.
Okay, Rinfer?
This component evaluates derivational validity, so the actual leaps of logic. And because logic is semantic, not mathematical, you can't just use a standard Python compiler to check it.
Right, how do you grade logic?
They actually use an off-the-shelf LLM acting as an automated judge to check every single derivational node in the graph.
Wait, really? So for every single and first step, this LLM judge looks at the established premises and the new conclusion, and it assesses the logical distance between them.
Exactly. It asks the hard questions. Does this conclusion logically follow? Did the AI quietly invent a new number in this text box? Did it make a massive speculative leap that the data just doesn't support?
And if it did?
If the logic is flawed, the AI gets penalized, even if the final answer at the very top of the tree happens to be correct.
That is fascinating. It's like training a dog to fetch a ball. Even if the dog brings back the ball perfectly, if it trampled through your neighbor's prize-winning petunias and broke a fence to get it, it doesn't get the treat. The process matters just as much as the outcome.
That's exactly it. And then finally, we have the third grade, rightcome.
Profound check.
Yeah, this is the terminal check. Assuming you built a perfectly valid graph with flawless code and sound logic, is your final answer actually correct? And does it faithfully answer the user's original prompt?
So we are grading the math, the logic, and the final answer completely independently.
Yeah.
It is an incredibly rigorous training environment. But I guess the ultimate test for you listening, someone who wants to deploy these tools in the real world to save time and increase accuracy, is how this architecture actually performs.
Right. Does it work?
Yeah. Does forcing an AI to meticulously build a family tree slow it down, or does it make it less capable of handling complex queries?
Well, the benchmark results completely validate the structural approach. The team tested VeriGraph on 4 intense data-heavy benchmarks.
What were they?
Table bench, DSetch, Infi-Agent bench, and DABI step research.
Okay, those are heavy hitters.
Yeah, these aren't simple trivia questions. They test everything from single-table fact-checking to multi-document financial research requiring really complex reasoning. And it's vital to note the size of the model they trained here. VeriGraph 8b is built on an 8 billion parameter foundation, specifically Qwen3 8b. In the world of modern generative AI, that is a remarkably lightweight model.
Oh, absolutely. For context, some of the major open source models out there are 30, 70, or even 400 billion parameters. An 8 billion parameter model is something you could almost run locally on a high-end laptop. It really shouldn't be able to compete with the giants.
Yet, VeriGraph 8D achieved the highest overall score among all the evaluated baselines across those benchmarks.
Wait, it beat the big models?
It didn't just beat models in its own weight class. It matched or outright beat proprietary behemoths like Claude 4.5 Opus, GPT 5.2, and massive 32 billion parameter open models.
That's incredible.
It punched incredibly far above its weight class purely because of its structural discipline.
But the metric that truly defines the success of this paper, the one that solves that hallucinated Q3 revenue problem we started with, is the grounding rate.
Yes, the grounding rate.
The paper says VeriGraph achieved an 87.61% grounding rate. That is a massive 14-point jump over the absolute best React baseline they tested.
Yeah, and to put that into perspective, an 87.61% grounding rate means that almost 9 out of 10 factual claims in the AI's final answer can be perfectly mechanically traced backward through the graphs directly to the raw data sources.
9 out of 10.
Yeah. 87% of the time, the facts are definitively proven by executable code and audited logic. With the older linear agents, even when they managed to guess the correct final answer, their grounding rates were hovering in the 60s or 70s.
So you just couldn't trust the work they were showing you?
Not at all.
There's a really fascinating nuance buried in the paper's latency and cost analysis that highlights exactly why this approach works so efficiently. You would assume that forcing an AI to build this complex, multi-layered graph would eat up massive amounts of processing power and token budget, right?
That's the natural assumption, yeah.
But VeriGraph actually spends more of its token budget on writing code and executing actions, and significantly less of its budget on unconstrained natural language reasoning compared to standard agents.
It is a brilliant resource allocation trade-off. It basically shifts the heavy computational lifting from deliberation to executable programs.
Right.
Standard linear agents waste thousands of tokens just rambling to themselves in their internal monologues. They use a process called chain of thought, where they constantly have to remind themselves of previous facts to keep everything straight in their context window.
They're essentially just thinking out loud in paragraphs just to keep their memory fresh.
Exactly. But VeriGraph externalizes that memory. Because every single fact, computation, and premise is securely bound to a specific node in the graph, the AI doesn't have to keep repeating itself in its context window.
It just looks at the node.
Yeah, it just references the node.
Yeah.
It trades a tiny bit of latency for massive structural integrity, thinking in math and localized logic rather than just rambling paragraphs.
So if we pull all of this together and look at the bigger picture, I mean, in an era where every major tech company is constantly screaming about their new, supposedly flawless AI, why does this specific paper matter so much?
It matters because it proves definitively that evidence structure must be a first-class optimization target in artificial intelligence.
A first-class target.
Yeah. For far too long, the AI industry has treated explainability as a post hoc afterthought. The standard operating procedure has been to build a massive opaque black box, train it to spit out an answer, and then try to paste an explanation onto the outcome after the fact.
Which we know doesn't work.
Right. VeriGraph proves that if you force the AI to construct the audible proof while it solves the problem, you don't just get a more trustworthy system, you actually get a smarter, more accurate system that requires a fraction of the raw computing power.
And for you listening, whether you are prepping for a crucial boardroom meeting, you're analyzing emerging research in a new scientific field, or just trying to optimize your personal investments, the baseline for being well-informed by AI is shifting.
It absolutely is.
We are entering an era where demanding tools that simply give you an authoritative-sounding answer is no longer enough. The future belongs to tools that give you auditable proof. You should never have to guess if an AI hallucinated a vital statistic. You should be able to click on it, follow the branch down the tree, and see the undeniable math for yourself.
Because trust in automated systems can only be earned through that exact level of mechanical transparency.
Absolutely. Which leaves me with a final, slightly provocative thought for you to mull over as we wrap up today.
Oh, let's hear it.
If we successfully scale this technology, if we train AI agents to perfectly map out every single logical leap, every computation, and every premise in a flawless, interconnected evidence tag, will human analysts eventually be required to present their reasoning the exact same way in order to be trusted?
Wow.
Or are we building AI to a standard of verifiable mathematical logic that our own messy human brains aren't even capable of matching?
That is a fascinating question.
It really is. Something to think about the next time you hand in a report. Thanks for joining us on this deep dive.